Going back to one of my older math videos, one of the most interesting repetitions of 1 divided by 7 and the 142, 857 series is the idea that any number can be automatically divisible by 7, such as 112 or 28, if we extend it using zeros to a certain amount, that it would still be divisible by 7 itself. For example, let's start with the basics. The number 112. Let's put zeros in between the ones, so we have 6 zeros in the middle. So that essentially becomes 1,000,000,000,012. And if we divide that by 7, we get 1,014,285,716. Because this so clearly exists, we can use this base and customize any number divisible by 7 and add any number within these zeros that is divisible by 7 to create divisibility and create sort of our own arithmetic modular math. And this works for any number divisible by 7, for example. So to put this in the literal translation, let's put 14 between our large number 1,000,000,000,012, and we get 100,140,012. And thus we go. It is divisible by 7 still, and we get 14,305,716. Now we can hack any number at that point that is divisible by 7, or so change it with a certain amount of zeros, and it will still be divisible by 7 regardless of how many zeros, because usually any zero would mess up divisibility, such as 102 to 10,012. Still doesn't work. But usually in this case, since there's 6 zeros exactly, it's still going to be divisible by 7. So let's take the number 600,012. In division long step, it's simply 5,999 and 112 when dividing step by step. We can use that 112 to extend it and insert any number divisible by 7 to create a number that is still divisible by 7 and sort of create our own 1 over 7 series number. The original number with the extended zeros would become 6,000,000,000,000,000,000,12 with 9 zeros. And when dividing that by 7, we get our 1 over 7 number in the middle becoming 8, 571, 428, 571, then 6. If we add more zeros, this 714,285, a number simply repeats more and more again. So for example, 6, 0,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,12 with 15 zeros becomes divisible by 7 regardless. And that becomes this really large number, which I'll put that on the screen. But let's keep it basic, and we're going to craft a pretty large number here. So let's keep a number basic and keep to the one with 9 zeros. And let's insert a number that is divisible by 7, which is 1,855 somewhere there. So if we put it in an obvious position, we get the number 600, 185, 500, then 012. I'm not saying the full number because it's going to take too long trying to pronounce it for the video. But for math nerds, it looks painfully obvious. 60,018 is our first chain right here. That's divisible by 7. Then we get the number 55,000,012, and both by default are divisible by 7. Once we divide this really large number, 600,185,000,012, we get the answer 8,574,078,5716. Now, let's focus on the 55,000,012 part, and notice that once we notice in long division, we notice that that 66,000,012 chain is again there, step by step in division once we see it. And that's an easy. Let's make that even bigger, and let's add 6 zeros at this point. So this becomes 55,000,000,000,000,000,012. This time, let's inject a 3 number that's divisible by 7, and we'll choose a number 413. Now we have the number 55,000,413,000,012. Divide that by 7, and we get a large number that I'm going to list on the screen again. And now our goal here is to plug in this number to our previous large answer, which was 600,18550,000,012. So now it becomes an even bigger number, 600,185,000,000,413,000,012. Divide that by 7, and we get this unusually large number again. And this is in part consequentially because of the 1 divided by 7 division. And add any amount, a certain amount of zeros to any base number divisible by 7, we create infinite chains of divisibility by 7 for that given number. And if we customize it, we can add any number divisible by 7 in any of these zeros and get our own little number. And we can even customize 55,000,413,000,012 and make it even bigger. Because when we look at that 13,000,012 chain, only adding 7 and 14 position that are just right. And essentially, 13,000,012 is essentially in long division 7, and that same number 6,000,012. But our goal here is to put 7 and 14 in any of these random 0 positions. If we break it down, it's practically that, as I said. So let's make it 6,007,000,14,000,012. We divide that by 7, we get that really large number again. Now let's plug this into our large number already. So now it becomes from this large number into this behemoth of a number, 600,185,500,000,007,000,14,000,012. And surprisingly, again, using this infinite 1 over 7 thing, divide that by 7, and we get this really large number. And to any typical math thinker, this metaphor, that's practically a 30 millimeter U-lock when one tries to break it down too closely. But it proves again how the 1 and 7 and 142, 8,057 series change the math when it comes to being divisible by 7 per any positioned amount of zeros. It's addition combined with customization practically. But to make it simpler, let's focus on the number 400,008. It's divisible by 7 and we get 57,144. Let's change our position and add some 7s in between this number. And we're going to extend this again by 6 zeros. So this becomes 4,000,000,000,000,000,000,000,000,8. Divide that by 7 and we get that same 1 over 7 number in between 57,144. So we get that. To customize it simply, let's look at this unusually large number and let's put a 7 right near the middle so that we, in long division, trigger that number 40,005, which itself is divisible by 7 upon step-by-step division. So it transforms into 4,0,0,0,7,0,0,0,0,0,0,0,0,8. But we break it down and let's focus on the remainder of 2 after that first initial division step. And we get the number 2,000,000,0,0,0,0,8. It's already divisible by 7 because of that 112 trig we said here, but our goal is to add a 7 somewhere there and divide it again. So I want to put it near the end, so I put my number as 2,000,000,0708, so which itself is divisible by 7, and we get the number 2,857,244. Now let's plug in that 7 into the larger number here, so we get the number 4,000,007,000,008. We trigger that same two 2,000,008 sequence right there. And looking at that again, divide this number by 7, and we get our really large number again, and which is 57,152,857,244. And it remains divisible by 7 again. When dividing step by step, it's practically that same number, 399, and then we get our number 105, then 2,000,00708 when looking at it step by step. But to break it down a little bit more, let's grab the number 1,776. It's divisible by 259 because 776 plus 1 is equal to 777. Divide that by 3, it's 259. So this number, 1,776, which itself is divisible by 7. This time, let's extend the zeros between 1,776 and insert 259 itself somewhere there. I want to put my zeros in between the 7 and the 6, so we get our number 1,000,077,000,000,006. Divide that by 7, we get this really large number again. But this time, let's plug in 259 all the way at the end. So this time we get 1,000,770,000,2596. Divide that by 259 itself, which is divisible by 7, and we get this large number again. And surprisingly, for the number 259, it is still divisible, given that 1 divided by 7 sequence again. And our final examples, because there's so much I want to present, but I don't have as much time because of my own given laziness. Let's get to the number that we talked about before. This one is 2,000,096. Divide that by 7, we get 285,728. I want to keep this little number repeating forward, so let's add 2,107 in the middle to keep that division going somewhere once we extend by 6 zeros again. So after extending 6 zeros, let's plug in 2,107 near the beginning again. So this time we now have 2,002,107,000,096, and we get that same number again as we've spoken from the beginning, and it's divisible by 7, becoming 286,015, 285,728. This works for about any number that is divisible by 7. Let's take the number 400,981. Add 6 zeros, 7 in the middle. Now we get the number 4,000,007,000,000,981. And let's say for the number now, this time to a larger one, 16,000,000,512. Let's add more zeros and we'll insert 2,807 in the middle. Now this time we get 16,002,807,000,000,512. Divide that by 7, we get this large number again. And yet it is still divisible, which shows that it's modular arithmetic addition. And it just works because this is repeating zeros, all because of that 1 over 7 number series, because it can be applied to any number divisible by 7, such as 224, 896, 1792, 196, 392, 112, 5999, 238, or even the number 119. It will mess with the brain a lot in getting the zeros right, but with enough practice, you could customize your own large number that's still divisible by 7 and treat it as Lego blocks. And the core mechanism about this is still fundamentally linear. Add 6 more zeros to a given number divisible by 7. Add any number divisible by 7 into that chunk and customize your own 142,857 series number. That's just arithmetic addition. And before this video is to conclude and I'm going to lose out on more sleep, try the number 1,099. Add 6 zeros in the middle, but this time add a 14 in the middle. So we get the number 1001400099. And try it out by 7. Use a really large calculator for this because it's going to require a little bit, and it's still going to be there.